Hi guys, again. This is the final geometry lecture, I think. Yeah, I've got one more lecture after this, but this is the final geometry lecture. Just something from the test today. These handling sketches, like, I need to be able to see what I'm doing. And then secondly, cases. Cases were hugely important in today's paper. A lot of you did the second case, but there was also another case that you had to continue looking at. And so, yeah, just watch out for that. Right, so felt like today I should do something more standard. So I'm going to talk about the 9-point circle, and I'm going to prove the 9-point circle, and maybe we'll look at something after that. Right. You have a triangle, A, B, C. If you draw the altitudes that intersect at the orthocenter H, so these are 90 degrees here, we get the feet, HA, HB, and HC. And if you write the midpoint of the sides, so MA is the midpoint of AB, of BC, MB is the midpoint of AC, and MC is the midpoint of AB. Then, and also finally the midpoints of the lines AH, HB, and HC. All those 9 points lie on a single circle. And we are going to prove this right now. So we will draw a smaller diagram so that it's easier to see. Start with facing this circle, and we'll just say that. Points. This is what? HB and E and A H A. And so first thing first, we are going to show that these 4 points lie on a circle. And we're going to do this by simply just chasing some ratios. First thing first, we will do this line and this line is parallel by midpoint theorem. So this angle here, ACB, is equal to AMB, MA. Sorry, that's not MA. C. And we're going to then connect it here. Now, HB, HC, BC is going to end up being a cyclic quad because CHCB is 90 degrees and CHBB is 90 degrees. So we have angles subtended from a common chord, which means that CHB, is a cyclic quad. And that means we have exterior angle of a cyclic quad. So we have AHC, HB is equal to AHCB. And then we have AMB, MC is equal to AHC, HB. So MB, MC, HC, HB is a cyclic quad using the exterior angle of a cyclic quad. The converse of that, right? Cool. So the converse of the converse, the slightly other case that you have to do in this case is when you have the two altitudes that are closer, or they're on opposite sides or something. Yeah. So if you have instead something like HA, MB, HB, MC, sorry, MA, then instead of getting the angles here, you're going to get them angles subtended. So what you're going to get is you're going to be chasing this angle and this angle will be the same. So just importance of cases. Right, and this can be generalized for all 6 ones. So we end up with, sorry, not 6. Is it 6? I think it's 6. Well, let's just write them out anyway. So we get a whole bunch of cyclic quads, and let's list them. So we get MB, C, HC, H, B, we'll get, and let me just make sure I have the order, so that'll be HA, that'll be MB, MA, and then we'll get MC, HC, HA, and A. And we'll get the next one there, which is HA, MA, HB, and MB. Right. So notice that these only have 2 points in common between any two of them, and that's not enough to claim that they all lie on a circle. So we need to get a little bit clever, and we need to find another point that will presumably lie on this one, that is in this one, and then we'll have that. So we should pick either one of the midpoints or one of the altitudes. Anyone have any suggestions? Anyone? No one? Okay, well, I think the best way to do this is to show that the all these circles have the same radical axis, all the points or something are the same. So let's look at the powers of certain points with respect to these circles. So C, for instance, the power of C.
Say the radical axis is AC and is CV and is AB, as it's the common chord.
Sorry?
Are you trying to find the radical axis of the circle?
Yeah. So
just say it's AC.
Precisely, but the idea, I think. Oh yeah, sorry, you've got a really good thing going on there. So if we consider the circle MA, HA, HC, MC, and the circle MB, HA, MA, HB, MB, the obvious radical axis is going to be MA, HA because it's a common chord, right? And so that means that this is the radical axis of those two circles. But if we then consider the radical axis of, so we've done these two, and we get that the radical axis is, okay, let's just give these some names, big names or something. Say, call this one big alpha, big beta, and big gamma. Then we have alpha, and beta. We have the radical axis is, what was it, BC? No, hang on. That one and that one was those two, so the radical axis will be AB. And then this one will give us BC. Oh, this is complicated. And then this one will be CN. This is quite convenient, and I'll explain this in a second, because I don't think I got to this point when I last did radical axes, so we can go over this. If we look at, yeah, so just to recap, we'll get this one, and these ones to be the radical axes. Now, if you have three circles, they actually have something called a radical center, where the radical axes of any pair of these circles will meet. And I think it doesn't require that much proof. If you have two circles like this that are separate, and you consider their radical axis, and you have, say, another circle, then the radical axis of the one will do this, and the radical axis of the other one will do like this. But we know that there's going to be a point with respect to these two circles where the power is going to be the same. And there's going to be a point on these two power circles where the power is going to be the same. And where that line intersects, we know the power of these two circles is going to be the same, which means the radical axis must pass through this point. But these three lines don't intersect at a point, which means these circles can't be distinct. At least two of them must be the same, and that gives us the third one. So that gives us all these points not cycling.
Wait, so these should have the same radius. Doesn't it just give the concentric? Or is that sufficient?
No, it gives them this. Sorry.
If the circles are concentric, they also
Yep.
don't have a radical center. Anyway, let me repeat one.
I think they do.
Okay, no, yeah, it's fine.
I'll think about that. Look at that. Think about that. But I still think they do have a radical center. Right. So we now have all those 6 points. So we now just want these last 3. And for this, we're going to, I think, use this diagram because they're very nicely drawn. So let's consider this midpoint here and assume it's not on the circle, or let's just not assume that it's on the circle, and just look at the angle that's there. And then what else do I want to draw? Actually, hang on. Maybe let's do the ortho. And we're just going to chase some angles until this thing comes up nicely. Let's draw HB. Right. So, any idea how we're going to get HB, XA, HC? Anyone? Okay, cool. So, is there anything special about XA? What do we know about XA? It's the midpoint of a line here. Does that make it special in some way? Someone gonna say something? No. We know that HCA is 90 degrees, so we know that AH is a diameter of the circumcircle of AHCH, correct? I think that's called Thales' theorem. Just a quick name drop. So if XA is the midpoint of AH, we know it is the center of the circumcircle of AHCH. And more importantly, we know that HB also lies on the circle because HB is also 90 degrees, so opposite angles sum to 180. It's like a quad. So this is the midpoint. Sorry, it's the center, circumcenter of this of the circle that goes around these 4 points. So that means this angle is twice this angle, correct? So if this is x, then this here is 2x. Right, now we need to start chasing this a little bit more. And I think the first thing we have to do is we need to look at the 4 points A, HB, HA, B, because we know that is a cyclic quad because AHAB is 90 degrees and AHBB is 90 degrees, which means we have 2 angles subtended by AB, which means a cyclic quad, and that means that we have external angle of a cyclic quad, which means that angle there is x. And I think, moreover, we have that in AHCHAC, which is a cyclic quad by the same reason that the other one was, we can do external angle again. So CAHC is going to be equal to BHAHC. So that's x. And then angles on a straight line gives us that HB, HA, HC is 180 degrees minus 2x. And that means that HB, XA, HC, HA is a cyclic quad, or more importantly, XA lies on the 9-point circle. And then similarly, XB and XC lie on the 9-point circle by the same reason. Okay. So there's an example of the 9-point circle. It's quite useful. And I think I'm going to do an interesting property of the 9-point circle, and then also demonstrate, actually, is homotopy actually even necessary? Oh well, if it's not necessary, it'll be overkill, but it's still sort of demonstrates the point of scaling. Right, so suppose we have a triangle with okay, so we have a 9-point circle, and I'm going to say that's H, C, H, C, H, B, M, B, M, A, H, A. And so this is a circle, so it has a center. We're going to call that N, because why not? And we're also going to actually have to draw in the authors for this because that's going to be important. That is not collinear. Yeah, not concurrent, which is not super great. So I'm going to have to fudge this a little bit to make it look. Okay, imagine those are straight. And that comes to the side.
The very notion of what it means to be alive.
Yeah,
So this is electron postmodernism.
yeah. They like to live on the edge. No pun intended.
Don't lie, it wasn't there.
Actually, it really wasn't. Right, okay, cool. So that's, I think, all the constructions I want to make. So the reason why I made these constructions is because I want to show you a nice property about the diameter of the 9-point circle, or the radius of the 9-point circle. It's got a particularly interesting feature. So let's look at this length here and this length here and find like the relations between them.
And
So, yeah?
midpoint between A and H and N and MA are also very collinear.
Sure. So we look at this angle here. I guess we should call this a name. What should we call it? Let's go with U. So CU subtends the angle CBU, which is also CAU. This is 90 degrees, recall. And we have that sorry, is that an HA? AHB, HAB is a cyclic quad, so we have that angle. So we have 90 degrees, angle, and a shared side. So we have two congruent triangles. So this line is equal to this line, and then for the same reasons, this line is equal to this line, and finally, this line is equal to this line. Is everyone clear why we can say these two are equal and these two are equal because we've done it for this case? Cool. Now, what does that look like to you? As Cajelo was doing? That. Yes, it looks like a homopathy with convenient center H. Right, with factor 2. So that means if we consider the homopathy H, center H, ratio 2, we have that. I guess I should give this 9-point circle a name. Let's call it omega 9, because why not? And then this is the circle, let's call it gamma. This implies that omega 9 goes to gamma. Can everyone see why that's true? Because if I take a circle, we know it goes to a circle. And if we consider just this triangle, HA, HB, HC, we know it goes to the triangle U, be W, and since circles go to circles, the circumcircle will go to the circumcircle, so omega 9 goes to gamma. And since we have a factor of 2, we know the radii are only a factor of 2. So that means the radius of a 9-point circle is equal to half the radius of gamma, which is quite interesting. Nice property. You can quote that as well, write it down and everything. And I think that's all I want to do on the 9-point circle. I'll just make one remark on the 9-point circle. I'm not going to prove it, but it's interesting. And it's got a theorem name, so you can quote it. So theorem. Might have spelled that wrong. So this is called Feuerbach's theorem. So the 9-point circle is tangent to the incircle and the 3 x circles of the triangle. Now I know you know what an incircle is. Is there anyone that doesn't know what an x circle is? No? Okay, cool. You guys all know. That's great. Yeah, that's quite interesting. And it's also commonly known as the 13-point circle theorem, because you take 9, you add 4, and you get 13. Right. So that's all I want to say about the 9-point circle. And then I have 25 minutes, and so I guess what we can do is we can talk about cases. Presumably you've all got this down now. It's been up for, I don't know, like 20 years. So, why are cases important? Cases are important because when someone asks you to prove a problem, you need to solve the whole problem, and sometimes that problem has multiple cases, which are hiding. This happens very often in geometry, and the biggest culprit of these is points on a circle. When they change, you get reasons changing, you get angles swapping all the time, and so we introduce something called directed edges and directed angles. Directed edges are less important, but directed angles are phenomenally important. So, generally what happens when you have a directed angle is you introduce an orientation at the beginning of your proof. Generally anti-clockwise, but can be clockwise depending on how you favor it, or if you're left or right-handed or whatever. But you must make sure that you remember that you've introduced an orientation, and it is very important with your angle names. So the most important thing about a directed angle, which will be indicated like that, so that's quite an important thing. And the reason why this is important is because, say you have a circle and you have some fixed points on it. Yeah? A, B, C. And you have a variable point x. want to look at these two angles opposite each other. Say let's call this, I don't know, x and y. And then say we can move x around. So in some other format of this problem, we will have A here, C here, B here, and then maybe x is over here. Now, I'm going to make sure that my orientation is anti-clockwise. So let's look at, we want to go anti-clockwise, which means we want to go that way, which means we start at A, B, and then C. So angle A, B, C, plus, and then anti-clockwise again, so that way, angle C, X, A, equals 180 degrees, because cyclic clock. This is fine, we all know this. But over here, in this case, we have angle ABC plus angle CXA is equal to 2 times angle ABC, because they're subtended from the chord. But when you introduce directed angles, you have the same thing on this side. But on this side, we get something slightly different. Because if we now look at our orientations, ABC, we're going that way. Cool, so that's fine. But CXA, that's going this way. That's clockwise, which means that we need to take 180 degrees and subtract that. So this is equal to ADC plus 180 degrees minus angle AXC, which is then equal to, well, we know AXC is equal to ABC. So these two cancel. And so we're left with 180 degrees. See why that's important now? Cool. Now, let me show you why this is important for today's problem. So I'm going to draw 2 cases. We're going to have B. I can't actually remember what the question was. Hopefully, no, this is not. Yeah. And so we've got M and N are the midpoints of AB and CB. So M, N. And let T be the intersection of the line from M perpendicular to AC. So that's there. And I think we drew this one as well. These are 90 degrees. And then this point is called T. And then we have to show that Tn is equal to the radius of the whole circle, of the circumcircle of ABC. So let's draw the circumcircle in here. Circumcenter, sorry. Cool, so that's the circumcenter. So ON is a perpendicular bisector. Let's see, ON. Right. So you guys see why OM is 90 degrees, right? Perpendicular bisector because it's center to midpoint. Same there, center to midpoint. So we have OMB. N is a cyclic quad. And if we chase some really minor angle, we're going to get that T also lies on this cyclic quad by looking at T, B, C, and then this point we're going to call it something like K. So T, B, C, K, we have CKT plus CB. Well, or should I say, if we introduce directed angles, we have with anti-clockwise orientation, we have angle TKC. No, that's not quite right. CKT. We're going that way, and then on this way we're going that way. So that's TBC equals 180 degrees, and so we have that cyclic quad. Now, this was where a lot of people fell flat, because in another case where, say for instance, B is obtuse, and also when A is obtuse, we get a slightly different looking result. So we get this perpendicular down there, so we'll draw down there, and then the perpendicular to M, this is A, this is B, this is C. Now, as you can see, in this case, if you decided to go with opposite angles of supplementary, in this case, it's angle subtended. So as much as you would have said something like this angle plus this angle is 180 degrees, in this case it doesn't mean anything. It only means something in this case. So what, this is T, I think. So that means that. But if we look at what this means over here, we will have that angle CKT, C, what's K again? K is the split here. CKT which is going like that, which is clockwise, so that's going backwards. And then TBC, that's anti-clockwise, that's fine. Then equal to 180 degrees minus angle TKC plus angle TBC. Now, in this point, it's a little bit trivial because we're looking at 90 degrees and stuff. So this is the same thing, but we've got that 180 minus 90 plus 90 is still 180 degrees. But because we're using directed angles, this, when actually looking at different things, this anti-clockwise angle here actually is this thing here. And this is a very weird looking special case of external angle. It's just with a cyclic quad that is sort of been twisted around. So you can actually save a lot of time and effort just by introducing directed angles. And I think that if you keep going, you also run into another problem, because you chase, once you've chased this angle, you then look at this angle here, which is equal to this angle here, by external angle of a cyclic quad, K, C, B, T. However, in this case, you're looking at this angle here and this angle here, so it's supplementary angles. So looking at it again, just to show you the consistency, in this side we have angle, which way is we going? We're going anti-clockwise, so BCK. Plus, not plus, is equal to, in this one we're also going this way, and okay, so now, I don't actually have something here, and where I would usually create a point, I could just say that that is the same as going this way. So that's BTK. And in this case, what we have anti-clockwise, so we're going that way, and this one is that one, and so BCK, and then BTK, so BTK, which as you can see is also anti-clockwise, so it's preserved. And then once you have that, again you have, here you've got parallel lines, use the midpoint theorem. And then from here you can see we've got the external angle of a cyclic quad, which will again follow the same principle as this. So once you've got that, you've got that TMNB is a cyclic quad, but OMBN is a cyclic quad, so OMTBN is a cyclic pentagon. And from here, we're going to, I think, just chase some angles or something and determine that OB is equal to TN by, can't actually remember, something like a, what's the word? Congruent triangle approach. So chasing the angles, what are we going to get? Sorry, was someone saying something? Oh, no, just talking to someone else. Let's take a look at this angle here. Yeah, let's take a look at that angle there. And that angle is equal to this angle here. And we want to look also at this angle here. I should actually probably label these nicely. Take a look at this angle here, double line that one. And that is equal to this angle here. And then vertically opposite angles, we have this one here. And so now we want to show that these things are all the same. How? Can we do a chord approach, or how do we do this now? I can't remember how to do this. Right, okay, so slight cheat and also introduction of some knowledge, I guess. We'll draw the altitude from B onto AC. I should probably write down this theorem somewhere, so you guys should take note of this. I don't know if this theorem has a name, but if you have in triangle ABC with circumcenter O and orthocenter H, angle, let's go with CAH is equal to angle OAB. So I'll draw a diagram for you guys. You can see what it looks like. We have orthocenter and circumcenter, OH. So CAH equals OAB, like that. And then thus you can also determine quite easily that magnitude of that angle. But you can claim that in a little bit. Oh, yes, question.
Can't you say that OB and NT are both the diameters in that circle?
Yes, that's the one. That's how I did it. And how you did it just now. Yeah, so that's very obvious. Thank you for that. Can everyone else see that? Okay, so just to explain that again. So OB subtends an angle of 90 degrees. And TN subtends an angle of 90 degrees. So they're both diameters, which means their lengths are equal, which means TN equals OB. Remember that. Right, and I'm running out of time. I've got 5 minutes. And since I guess I can take some questions on directed angles, because if there isn't, I would be quite surprised. But yes?
You have to use directed angles on the whole of it only for
You don't have to use it all the time, but you do have to use it when things change. So in a lot of the time, you don't have to use it, but for this proof, if you're chasing angles specifically in cyclic quads, you really do have to be careful because you get this thing where these things rotate past, and obviously the reasons don't work anymore and it doesn't make sense. With 90 degrees, if you're chasing lots of 90 degrees, you can state at the top of your proof that directed angles don't make a difference because 180 minus 90 is still 90. But if you're chasing anything that isn't 90 degrees, you need to be careful. Because otherwise you're just proving one case. And it is possible that you can get cases where if you don't use directed angles, you are just proving something that's just straight up not true, even though it kind of looks like it's not true. In this case, it's more of just making sure that your reason's right. But for instance, if you recall the question from, I think, day 3 or day 2, the one with the circle and the tangents, and you had to show that it was tangent to the circle on the inside. If you take the angle bisector of that particular angle, and it's not on the far side of the triangle, if it's on the closer side, then your angle actually ends up being, the point doesn't lie on the circle that's tangent to these 2 points, very close to the T. It lies on the circle that's tangent to the circle and those 2 things on the other side. So the statement's still true, but you're proving a different thing. And that can be confusing. So this is why directed angles are important when you're dealing with things like points on the circle. And in locus questions as well, if they give you variable points moving around the circle, directed angles, or just assert that there is no other case. And sometimes it's enough just to say that if you don't use directed angles, that the other case is symmetric to this in the sense that the thing's still going to be a cyclic quad, but it's just going to be the other reason. But you need to actually make the distinction that there is another case and list all the cases that there are. So for instance, today I've got 2 cases. So if one is acute or if one is obtuse, but in the case that one is acute, there could be another angle that's obtuse, and that was a separate case. And that's why directed angles were useful for today's question. Yeah, okay, so any more questions on directed angles? No. Is there anything, I've run out of syllabus now, so is there any questions regarding all of geometry that anyone wants to ask? Yes?
So can you use the congruency symbol for that?
Congruency symbol?
Yeah, because it's like, instead of saying ABC equals 180, let's see the ABC equals 180.
Yeah, okay, so when you talk about congruency and, well, I guess more importantly similarity, because congruency is just a special case of that, things get really complicated because when you talk about, say, 2 triangles that are similar, say one that looks like this, and then one that looks like, I guess we mark these sense, and then one that's much smaller. Then when you write the similarity, you need to make sure that your things are in the right order. However, if this thing is reflected, you've got weird things going on, and that's when directed angles sort of don't really work very well. So if things are going backwards, so in this case we have 1, 2, 3, in this case we have 1, 3, 2. And directed angles kind of not so great with these things because this flipping thing is not great. But an important thing is that homotheties, they preserve directed angles because you're either getting bigger or you're going through, but you're reflecting sort of both across and below, so your orientations remain the same. And also inversion, if you guys know inversion, directed angles also are preserved with inversion. And did I answer your question, or are you still confused? Because I think I might not have answered it properly.
Yeah, so I'm going to add to his question. I see in the competition that mostly it's solved by using similarity and very rarely there's ever congruency.
Yeah, so congruency generally pitches up when you want to, like, got these very, very special, lots of conditions and stuff like that. Similarity is way more important.
Yeah.
Chasing ratios and all those things. Yeah. And
Not directed angles, but similar to moving points in projective geometry is like a popular technique now with all the big line.
You mean like IMO questions using a particular, like moving a point in?
No, like the techniques for moving a point or something. It's on I don't really understand what it is, but it's popular now with big line.
Well, okay, so I've never heard of this technique, but when something is popular on AOPS, it usually means it's popular in Eastern Europe. And so, like, also not super useful. Like, I mean, generally, like these really, really high power things can kill problems really quickly, and if you're really, really good at it, yes, you have the ability to solve IMO problem 6s because you've worked on it for so much that the intuition just floods into your brain. You've seen all these orientations of lines and angles before, and you just go, yeah, cool, I understand what's going on here. But actually, most of the time, IMO problems are solved using clever uses of PowerPoint and being careful about cases. The amount of times where you have to be careful about cases is a huge deal. And yeah, so I wouldn't really bother so much with projective geometry if you're not comfortable with it, or especially if you're not really solidified with basic stuff. But if you're really comfortable with using a multi, really comfortable with using everything, and you've got nothing to do, yeah, sure, you can learn the stuff. I can look at it if you want and tell you if it's great or actually useful and stuff. Cool? Yeah. Right, I think I'm now out of time. So there should be drinks for you guys outside. If there's anyone who wants to come